In this 8th module, we are discussing two mysterious components of the universe, which are dark matter and dark energy. And in this 3rd video, we review dark energy. After following this video, you will know how we know about this new form of omnipresent energy and why its existence is still a matter of debate, and what are the main components of dark energy. To understand the signs of presence of dark energy, we must revisit the expansion mechanism of the universe. In the late 1920s, Hubble observed that the line spectra of distant galaxies are redshifted. This is because of the Doppler effect associated with their recessional velocity, v. The wavelength lambda prime observed on Earth is offset with respect to lambda, the wavelength in the rest frame of the emitter. The redshift parameter is called z equal to delta lambda over lambda. Using the redshift to measure the velocity v and the magnitude as an estimator of the distance r to the emitter, one empirically observes Hubble's law, v equal to h times r. Recessional velocities are thus proportional to distance, with a coefficient called the Hubble constant, capital H. Hubble's law corresponds to a uniform expansion of all distances, including all wavelengths, by a factor r of t, where r0 is the current scale at t equal to t0, which is today. Without loss of generality, we can normalize any distance to r0 equal to 1. Capital R then becomes a generic distance scale. The Hubble constant is given by the relative rate of change in r dot divided by r. Contrary to its name, h is not constant because of the decelerating effect of gravity on the expansion of the universe and the accelerating effect of dark energy. Today we find h0 roughly equal to 70 km per second per megaparsec, with an accuracy of a few percent, although the various methods for determining this constant give somewhat different results, as shown in the plot on the right. One expresses large astronomical distances in parsec. 1 parsec roughly equals 31 times 10 to the 12 kilometers, and is defined as the distance at which the mean radius of the Earth orbit around the Sun subtends an angle of 1 arcsecond. The evolution of the universe is dominated by the action of gravity since early in its history. It follows the solution of equations describing general relativity. For a homogeneous and isotropic distribution of matter at large scales, it is described by the Friedmann equation. The first term containing Newton's constant Gn and the mass or energy density ρ of matter describes the decelerating action of gravity. The constants capital K and lambda determine the asymptotic evolution. The cosmological constant lambda potentially corresponds to an energy associated with a vacuum, the so-called dark energy. For now, we neglect this term, although it may dominate the evolution of the universe today. If you are interested in the motivation behind such an equation, we recommend the small calculation in video 8.3a. The constant K corresponds to an intrinsic curvature of space generated by its total energy. There are 3 distinct cases. For K equal to -1, this corresponds to a total positive energy. This case describes a so-called open universe that extends to infinity, with r dot tending towards 1 for large r. In this case, the curvature term minus k divided by r squared is positive. For k equal to +1, corresponds to a negative total energy, a closed universe with negative curvature, which extends to a maximum radius and then shrinks. The special case, k equal to 0, is that of a so-called flat universe, where the kinetic and potential energy are equal, the total energy and thus the curvature are 0. The rate of expansion tends towards r dot equal to 0 on the long term. An inventory of the contents of the universe today shows a remarkable density similar to the density corresponding to k equal to 0. So we neglect this term. Integrating the Friedmann equation for the special case k equal to lambda equal to 0 and in non-relativistic approximation, a simplified expansion equation is obtained. From today's value of Hubble constant, we can derive T0, the age of the universe, which corresponds to 9.4 gigayears. This is well below the age of the oldest object we know about, which varies between 11 and 14 gigayears. Obviously, a negative k, or a positive value of the cosmological constant lambda, would lead to an increased T0 prediction by the Friedmann equation. Since k is roughly equal to 0, we need a substantial amount of dark energy to obtain a reasonable age prediction. For k equal to 0 and a cosmological constant lambda not equal to 0, the Friedmann equation acquires the last term. It corresponds to a constant energy density associated with the vacuum itself. This corresponding energy density adds to the matter density as shown in the second equation. Considering the equation of state, we see that this energy exerts an internal pressure on the expansion of the universe, as shown by the third equation. If lambda is larger than 0, this pressure is negative and accelerates the expansion, opposing the decelerating action of gravity. To understand how we measure the expansion velocity in the past, we must remember that the photons reaching us from a large distance were issued in a distant past. By observing the redshift of a characteristic line, we can measure the velocity of the emitter in the past. And it can be compared to that of a closer source from photons emitted more recently. For this, we need an estimate of the distance z, which is independent of the redshift. The observed flux f of photons can be converted into the luminosity distance dl if the emitted luminosity L is known. The luminosity distance is related to the astronomical magnitude m by the numerical conversion given in this formula. For a non-relativistic recessional velocity, we have v roughly equal to z. For a constant Hubble parameter, we thus expect a relationship m of z equal to a plus b log 10 of z between the magnitude m and the redshift z. Provided one can identify a standard kind of source with constant emitted luminosity L, one can then find a sample of mi at sufficiently different zi and test this proportionality. Thermonuclear explosions of type 1a supernovae are such a standard candle. Their brightness can be derived from the properties of the light curve, i.e. the photon flux over time. Measurement results are shown here with the log of the redshift, i.e. the recessional velocity, as the ordinate and the magnitude as the abscissa. Turns out that for large distances, the recessional velocity is always less than what is expected for lambda equal to 0. The expansion of the universe is accelerating. It is now faster than it was in the past. For this discovery, Perlmutter, Schmidt, and Ries have received the 2011 Physics Nobel Prize. But a word of caution is required here. The methodology providing evidence for dark energy is continuously under scrutiny. In a recent paper, Subisaka and his collaborators have analyzed a larger sample of sources. This plot shows the difference of the measurements of the straight line from the straight line in the magnitude redshift relation that we've shown in the previous slide. It is clear that the spread of the data is comparable, if not greater than, the expected effect of dark energy indicated by the blue line. No dark energy corresponds to the dashed red line. The authors conclude that a universe without dark energy is improbable, of the order of 0.3%, but it is not impossible. The universe today, therefore, probably consists of 26.8% dark matter, 68.3% dark energy, totaling 95.1%. This leaves place for no more than 4.9% of ordinary matter. The density of dark energy is very low. It's of the order of 6 times 10 to the minus 27 kilograms per cubic meter, such that the total solar system up to the orbit of Pluto contains only a negligible amount compared to the solar mass. But since its distribution is uniform, dark energy dominates the evolution of the universe at the cosmological scale. Different forms of dark energy have been proposed: an energy density filling space homogeneously, like the cosmological constant lambda, or custom-designed scalar fields which generate this effect dynamically. For a more in-depth discussion of dark energy, I refer you to the article by Ruth Dura cited at the bottom of this page. With this, we have almost concluded our tour of subatomic physics. If we compare to the reductionist program of particle physics, that is to understand the complete universe based on its microscopic properties, we realize that we have understood a lot about a small fraction of what is there. The many parameters of the standard model, the masses, or rather the Higgs couplings, the coupling constants to forces, mixing angles, etc., ought to be fixed by a more profound layer of theory. Unknown ingredients, dark matter on the side of matter, dark energy and inflation on the side of forces, clearly indicate that much of the universe remains to be discovered. And in addition, even how to integrate gravity into our microscopic model of the universe is far from clear. This leaves enough work for future generations of physicists, and why not you? In the last video of this module, we interview Professor Ruth Durer about her vision of dark energy.